Okay. Cross-validation, or can we get away with setting k equals to 1 in the validation setup? So cross-validation. Or can we use k equals 1? And we saw the trade-offs with k. So we're going to one extreme of the trade-off and trying to get g approximately equal to g minus. Okay, but then we're wondering whether the validation estimate is going to be of any use. So let me illustrate with regression, okay, which I can easily draw. But I want to emphasize that this whole validation framework and model selection applies to any machine learning problem: classification, regression, logistic regression, and whatnot. Okay, so here's a simple regression problem. You have 3 data points. Okay, so let's imagine 3 data points. Okay, and if you fit the data, you're going to get a line something like that. Okay, so one-dimensional regression. Okay, now if I'm setting k equals 1, I leave 1 data point out, and I'm going to fit on the remaining 2 data points. So let's imagine that I left out data point 1. So, let me indicate that by, I leave out data point 1. Okay, and I have the other 2 data points. Okay, and since this has been left out, I have to fit those data points. So my deficient hypothesis is going to be this guy. Okay, and I'm going to get an error, which is this guy. Okay, so this is the deficient hypothesis. This is, you can call this G1 of deficient. Okay, so if I call this data point x1, this data point x2, this data point x3, then if I leave out data point 1, I get the deficient hypothesis G1 minus, indicating that I left out data point 1. Okay, and I get an error across a validation error E1. So E1 is the validation error. Is E1. And it is indeed the case that if I take the expected value over the data point x1, that the expected value of E1 is equal to E out of G1 minus. That is true. Okay? That's the whole validation analysis. Okay? The problem with E1 is not that it has the wrong estimate. It's not that it's not estimating E out correctly. It's that it's wild. Its error bar is huge. So it's wild. E1 is wild. Okay? All right. But, nobody said I had to leave out E1. I mean, X1. Nobody said I had to leave out data point X1. So let's see what happens if I leave out, maybe another data point. Okay, so this is if I leave out data point X2. So I have this guy, that guy, and I've left out this guy. Okay, so I have to, my learning is producing the deficient hypothesis that fits the data that remains in the training set, which is this. Okay, and now I have an error which is E2, okay, and this is my deficient hypothesis G2 minus. The deficient hypothesis I get from leaving out data point X2. Okay. And so the validation error in this case is E2. Okay, and again, E2, the expected value of E2 is indeed expected with respect to the second data point is indeed E out of G2 minus. But it's just wild. And we can do the same thing with the third data point. Okay, so what happens if we leave the third data point out? So we have this guy and that guy, and we've left out this guy. So we have to fit these points. That's our training data. And we incur a validation error, E3. Okay, and this is my deficient hypothesis, G3 minus. Okay, and, so my validation error is E3. And it is indeed the case that the expected value of E3 with respect to the third data point that I left out is indeed E out of G3 minus. So what these mean is that, the data point that's left out is a random test point for the corresponding deficient hypothesis. Okay? But they're all wild. So which one should I pick? And the answer is, don't pick any of them, pick all of them. Okay? In other words, average. Okay? So on the one, so each of these is a decent estimate of the out of sample error for a deficient hypothesis. Now, okay, important. These deficient hypotheses are all slightly different. So you have G, this guy G, okay, and each of the GIs, GI minus, so G1 minus, G2 minus, G3 minus, and if I had endpoint, they're all sort of slightly different from G, and they're all slightly different from each other. Okay? But here's the interesting thing. I have out of sample estimates for the deficient hypotheses G1 minus, G2 minus, G3 minus. Okay? They are all close to G. So all these out of sample errors are close to the out of sample error for G. So let me take the average. Okay, and they're all wild on their own, but if I take the average, maybe I get a good estimate of the out of sample error for G. Okay, so take the average. And that leads us to the cross-validation, estimate for the out-of-sample error. I'll call it ECV. Okay, and this is equal to the average. I'll write it in the general case. So here we have just 3 data points. It's the average of, the leave one out validation errors. So it's the average of over little n goes from 1 to big N of E sub little n. So this is called the leave one out error for leaving out data point xn, yn. So it's the leave one out error. Okay. And I just get all the leave one out errors and average them. So that is my, cross-validation estimate of E out. Cross-validation estimate of E out. Sometimes it's called the leave one out error for this reason. Okay. Now, let's see what's going on. Each of these little estimates is an estimate for the out-of-sample error of a function that's close to g, okay, and then I'm just taking the average. In fact, theorem. Okay. So let me define, E out of n minus 1. Let me define E out of n minus 1. So what is that? That's the error you expect to incur when you learn with n minus 1 data points. Okay. It's the error you expect to incur when you learn with n minus 1 data points, averaged over data sets of size n minus 1. So you can think that, I generate a data set of size n minus 1, I learn, I produce a hypothesis g sub n minus 1, let's say, okay, and I evaluate its out-of-sample error. Okay. Then I repeat, generate another data set of size n minus 1, learn what's the out-of-sample error. And on average, I get some expected out-of-sample error when I learn on n minus 1 data points. Okay. So, theorem. If I take the expected value with respect to data sets, so with respect to data sets dn, my data set dn, for the cross-validation error, this equals E out of n minus 1. So in other words, the cross-validation error is an unbiased estimate of what? Of the expected error you incur when you learn on n minus 1 data points. Now, in reality, you are going to learn on n data points. Okay, you're going to output g. So E out of g, okay, because this is the expected error on n minus 1 data point, E out of g, you expect that to be slightly less than this. So typically, E out of g will be less than or equal to ECV. Okay, well, okay, because this is the error after having learned on n data points. Okay, ECV is an estimate of the error having learned on n minus 1 data points. Okay, and it's a pretty good estimate of E out of g because the k value, these deficient hypotheses, only differ from g by just 1 data point. So these are very close. Okay. And now the only question is, how wild is ECV? And we might think that the error bar is plus order of 1 over root n, because it's the average of n things. The problem is these n things are not independent, and I'm just going to leave it at that. Okay. And I'll just illustrate why they're not independent. So let's look at, for example, E1 and E2. Okay, E1 is, an error on data point x1, y1. Okay, so it's the error on this. E2 is the error, on x2, y2 for G2 minus. But G2 minus depends on x1, y1, which depends on x1, y1. So E1 depends on x1, y1 on the first data point, and E2 also, in a very subtle way, depends on the first data point x1, y1, albeit not that much, because G2 depends on n minus 1 data points. So the influence of x1, y1 is not very large on E2. Nevertheless, it exists. So E1 and E2, these errors are not independent. but they're almost independent. But I cannot give you a mathematical quantification of that. It's very hard to analyze theoretically the variance, for example, of the cross-validation error. But E1, E2, up to En are not independent. Okay, they are not independent, but they're almost independent. So you more or less, in practice, we see that we get, maybe not 1 over root n, but maybe we get like 5 over root n or something like that. It's very close to being independent. Okay. And so this is a very good estimate of the out-of-sample error, the cross-validation error. And so now you can use this error for model selection, okay, and get k equals to 1. So cross-validation, the queen of validation, is a way to get away with k equals 1. Okay. Now, you might wonder, well, in practice you hear people talking not about cross-validation, but about something like tenfold validation. Okay, so let me tell you what's going on there. So cross-validation. Okay, that is what you should do. Okay, and if the stakes are very, very, very high, then that is what you should do. Okay, the problem is it is computationally intense. So computationally intense. Okay, so let me show you what's going on here. Okay, so look what happened with just 3 data points. I have to run 3 linear regressions. Okay, and imagine if I'm doing not linear regression with the pseudo-inverse analytic algorithm, if I'm doing classification and I have to run the bucket algorithm for 1,000,000 iterations. Okay, so I have to, in general, with n data points, okay, I have to do n separate learnings and then 1 more to output the final hypothesis G. Why? Because I'm never going to output one of the deficient hypotheses. Okay, I'm going to squeeze out that little extra blood, that little extra data points worth of accuracy. Okay, these deficient hypotheses and the cross-validation error, again, let me emphasize, it's just a way to get an estimate of the out-of-sample error. I'm still going to output my final hypothesis G. So I have, n data points, I have to do n plus 1, episodes, or n plus 1 separate trainings. Okay, n of those are on data sets of size n minus 1, and 1 on data set of size n. And typically, each training is not going to be less than, linear in n, and sometimes it can be even worse. Okay, so this is immediately an O of n squared, algorithm, process. Okay, and typically there's some exponential dependence on the dimension. So imagine if n is 10,000, this is already, 10 to the 8. Okay, so it can be, and that's heavy. It's very heavy. So, what does tenfold cross-validation do? Tenfold cross-validation says, okay, don't leave out 1 data point at a time. Leave out 10% of your data at a time. So if you have all your data, okay, you leave out 10% of your data. And so there are 10 separate 10%. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you leave out 10% each time. Okay, so and you could do instead 20-fold where you leave out 5%. Okay, so it's now getting closer to validation, except that in validation, you leave out 20% of the data and you're done. Here what you do is you leave out this 10% of the data. Okay, and you get a deficient hypothesis trained on here. So this is training. So then you get, let's call this the first fold. So you get G1 minus, and you evaluate it here. Okay. Then you leave this out and train on the rest, and you get G2 minus, the deficient hypothesis for the second fold. And you evaluate it on here. So you'll get E1, then you'll get E2, and similarly you'll get E3, E4, E5 up to E10. Now you take the average of those. Okay. So it has a slight advantage over just plain old-fashioned validation, which leaves out just 1 set and then goes. It's still the case, it's still going to be the case that you're evaluating now, the out-of-sample performance of a very deficient hypothesis. Okay. So it's not close to G. You're 10% away in some sense. You're using 10% less data. Okay, but that's much more efficient. Okay. Instead of n separate trainings, you just do 10 separate trainings, much more manageable. There's another situation in which you can run cross-validation, and that's when you can compute the cross-validation error analytically. And you can compute the cross-validation analytically for linear models in linear regression, even regularized linear regression. So regularized linear regression, you can compute ECV analytically. So I encourage you to read the book if you're interested, and you should be interested, otherwise why are you taking this course? Okay? And what that allows you to do, if you can do it with regularized linear regression, you can compute this guy analytically. It means that you can compute ECV of lambda 1, ECV of lambda 2, and so on, and then pick the best lambda efficiently for linear regression. And so one thing to do for classification is to use regression for classification and pick lambda, let's say, in your regression for classification setup, okay, using the analytic formula. Okay, so go and look at that. And what we're going to do, okay, is we're going to go and look at some data. Okay, so I'm going to show you the problem. Let's erase. So let's see cross-validation in action. On the digits data, real data. Wow, what kind of a person is this who's showing real data in a theory class? Well, you have to link to real data because machine learning, while a theoretical discipline, has to be connected to practice. Because if you can't do things in practice, there's no point doing the theory.